All right, my good friends, welcome to Unit 3, the quantum model of the atom. This is the second installment. We're going to be doing calculations in this one, wave calculations. So if you don't have your calculator handy, go ahead and pause the video and let's get started. Here we go. Anyone who's ever been to the ocean knows that waves move at different velocities. How do you calculate the velocity of a wave? Well, we'll need to begin with a few definitions. The first one we want to start with is frequency. Frequency is the number of times that a wave passes a given point per second. Frequency is the number of times that a wave passes a given point every second. So if we have 0.5 or half a wave per second, that's half a wave per second passing a fixed point every second. A wave per second is called hertz. So the unit for frequency is the hertz. The symbol for frequency is cursive F, or sometimes cursive V, all right? So we can write it like this, frequency like that, or we can write it like this, cursive V, just like that, all right? Now, a couple of other things about this unit, and that is this. When we write frequency, what we really mean is waves per second, right? Or cycles per second, either one. But the point is that in calculations, waves simply disappears. And I'll show you what I mean by that in just a minute. So that means that we're going to be left with 1 over seconds. And another way to write that is seconds to the minus 1 power. So you'll often see frequency as second to the minus 1 power. I wanted to tell you that now because that'll come up later on. A second definition we're going to want to take a look at is wavelength. That's the length of the wave from the wave crest of one wave to the wave crest of the next wave. The symbol for wavelength is lambda. We write it like this. It's kind of like an upside down Y. That's the symbol for wavelength. It's called lambda. Now, to calculate the velocity of a wave, simply multiply the frequency by the wavelength. So velocity is equal to wavelength times frequency. Now, we've said before that if the wave happens to be the speed of light, we'll substitute, instead of V, we'll write C, right? So we would write this. If we were talking about electromagnetic radiation, C is equal to wavelength times the frequency, okay? So the general form is V for velocity is equal to wavelength times frequency. But again, if we're talking about electromagnetic waves, like visible light, for example, we'll use the C. If the wave in question happens to be light, visible light, or any other type of electromagnetic radiation, the velocity is this number. It's 3.00 times 10 to the 8th meters per second. Now that's very important. All electromagnetic radiation, including visible light, travels at the same speed, 3.00 times 10 to the 8th meters per second. Now, the energy of waves. In 1928, Max Planck was studying X-rays and discovered a very important relationship between the frequency of a wave and its energy. The greater the wave frequency, the greater the energy associated with that wave. For example, X-rays have a very high frequency, so they have a very high energy. In contrast, radio waves have a very low energy. Thus, the energy of radio waves is quite low. Max Planck quantified this relationship with the following equation. He said that energy in joules is equal to a constant, which he called Planck's constant, times the frequency in hertz of a wave. So this is a very important equation here because it quantifies the relationship between frequency and energy. Remember, this is a constant, right? So the higher the frequency, the higher the energy. They're directly related. Now, Planck's constant is this number. It's 6.626 times 10 to the minus 34. And look at that unit. It's joule seconds. You've never seen, it's not joules per second, it's joule seconds, right? So that's a very important relationship that we've got now, which is the Planck's equation. Energy is equal to Planck's constant times the frequency, which relates the frequency then to the energy. All right, so let's do a couple of examples. Calculate the wavelength of a photon if the frequency of the radiation is 2.3 times 10 to the 14th hertz. So we're being asked for wavelength, right? So a photon is like a packet of energy, right? So we know that the speed of light is equal to the wavelength times the frequency. And I can write it as C because this is electromagnetic radiation, right? A photon is light. So I'm being asked for the wavelength, right? I'm being asked for the wavelength. And I'm given the frequency in hertz. So what I'm going to do is I'm going to isolate what I'm looking for. I'm going to divide both sides by frequency, and I get speed of light divided by the frequency is equal to the wavelength, just like that, right? So I know that the speed of light is this number, 3.00 times 10 to the 8th meters per second. And I'm going to divide it by the frequency that I've been given, which is 2.3 times 10 to the 14th. Instead of writing hertz, I'm going to write this as seconds to the minus 1. All right? Seconds to the minus 1. Because I want to be able to cancel. So what's going to happen is, now I'm going to need my calculator. So I'm going to say 3.00 second EE8. If you don't know how to enter scientific notation, ask me or ask someone next to you and let them help you. By the way, this was 2.3 times 10 to the 14th. So we'll divide that by 2.3 second EE14. And I get this number, 1.3 times, now let's talk a little bit about significant digits. I've got 3 significant digits on top and only 2 on the bottom, so I can only have 2 significant digits. I'm going to call it 1.3 times 10 to the negative 6th, and the unit is, I'm looking for wavelength, so it's in meters. So notice seconds on the bottom, and seconds on the bottom is going to cancel away, and I'm left with meters only. So that's my answer. All right, let's take a look at the next one. It says determine the frequency of a photon if the wavelength is 6.46 times 10 to the minus 7th meters. Well, again, the speed of light is equal to the wavelength times the frequency. And I'm looking for frequency, so I'll divide both sides by wavelength. So speed of light divided by wavelength is equal to frequency. Well, what was the speed of light? It was 3.00 times 10 to the 8th meters per second. And I'm going to divide that by the wavelength that I've been provided, which is 6.46 times 10 to the minus 7. And again, that's in meters, right? So now let me do that on the calculator. It is 3.00 second EE8 divided by 6.46 second EE negative 7. The number I get is 4.6. Let's see, I've got 3 significant digits on top, 3 significant digits on the bottom. I can have 3 significant digits, so I'll call it 4.64 times 10 to the 14th. It's times 10 to the 14th. Now watch. Meters and meters cancel, leaving me with 1 over seconds. 1 over seconds, or second to the minus 1, is hertz. So I'll write my answer for frequency as hertz. And that'll do it for the second one. Let's look at the next one. It says calculate the energy of a quantum of radiation energy. It's just an amount of radiation energy whose frequency is this number, 6.03 times 10 to the 14th. Well, Planck's equation says that energy is equal to Planck's constant times the frequency, right? And I'm looking for the energy, and they're giving me the frequency. So energy is equal to Planck's constant, which is this number, 6.626 times 10 to the minus 34. And remember, that was joule seconds, just like that, joule seconds, times the frequency. And the frequency, I'm told, is 6.03 times 10 to the 14th. I'm going to write it as seconds to the minus 1, even though it says hertz, because I want to be able to cancel this unit with this unit to give me joules, right? So when I do the multiplication, I get 6.626 second EE negative 34 times 6.03 second EE 14, and this is the number that I get. I get 3.995 and so forth, but remember I've got four significant digits here, only three here. I can only have three significant digits, I'm sorry, the lesser of the two. So 4.00 times 10 to the minus 19th. Again, seconds and seconds to the minus 1 cancel, and so my answer will be in joules, just like that. All right? Next one. What is the frequency of a photon of a microwave radiation whose energy is this number right here in joules? So remember that energy is equal to Planck's constant times frequency. And I'm being asked for frequency, so I'm going to divide both sides by Planck's constant. I have energy divided by Planck's constant is equal to the frequency. What was the energy that I was given? It was 4.28 times 10 to the negative 14 joules over Planck's constant is 6.626 times 10 to the minus 34 joule seconds, just like that. And so what I'm going to be left with, let me deal with the units first. Remember, joules and joules are going to cancel away, and I'm left with 1 over seconds. So remember that 1 over seconds is the same thing as hertz. Let's do the calculation. I've got 4.28 second EE negative 14 divided by 6.626 second EE negative 34, and that's equal to, let's see, I've got 3 significant digits on top, 4 on bottom. I can only have 3 significant digits in the quotient, and I get this number, 6.46. 6.46 times 10 to the 19th, and remember that unit, it was 1 over seconds, so I'll abbreviate that with an HZ, just like that, hertz. Folks, that'll do it for this one. I'll see you on the next one. Thanks. Bye-bye.